Okay, so I just talked about some very abstract stuff, but in a down-to-earth way, what I'm trying to say is that usually any function that you can think of, usually polynomials or maybe sine x or some nice functions that you know of, all these can be represented as sums of sine nx, cosine nx, and maybe 1. Okay? So in other words, if you take any function, so that's what Fourier series is. Fourier series. And although you can say this in a more general domain, let's say you have a function defined on negative pi to pi. Okay. Then Fourier's claim is that this function can be represented as a0 plus a1 cosine x plus b1 sine x plus a2 cosine 2x plus b2 sine 2x. Okay, what's next? A3 cosine 3x plus b3 sine 3x plus dot dot dot. Now that should remind you of the Fourier series, right? It should remind you, not Fourier series, Taylor series, yeah. Right? Similar, right? You write down something as an infinite series and you just start with it and see if there's a way to get these coefficients. Okay? Except that contrary to the Taylor series where you plug in 0 and everything disappears and you just get this constant term, that doesn't happen here. If you plug in 0, cosine 0 happens to be 1. So they don't disappear, so that's not the way to get it. So that's Fourier's claim, that such and such numbers exist. Now we have to figure out how to get these numbers. How should we get it? Plugging in doesn't work. Any ideas? This should be a hint.
A, B?
Hmm?
Are you pulling out A and B?
No. Here, our A and B will be negative pi to pi. Plugging in pi or negative pi will still give you some non-zero values. By the way, cosine n pi, when n is even, it's always 1. That's what we figured out, right? But if it's odd, then you get negative 1, because cosine goes up and down. Sine n pi is always 0. That I drew a graph and convinced you that it's true. So if you plug in pi or negative pi, again, although sines disappear, cosines will still be 1 or negative 1, so you still can't do it. What could we do? Yeah?
Multiply by sine x?
Yeah. You can multiply sine x, sine or cosine, but then you have to do, yeah?
Integrate.
And then integrate. That's what you do. So, here's what you do. You take f of x and multiply it by cosine nx, and you integrate from negative pi to pi dx. Now, let's say fx is some given function. So let's say fx is, say, x or x squared or whatever. Okay? Then you can definitely compute this for some given n. Right? That's not impossible. You can do it. You get some value, which will depend on n, but you could. So I'll give you an example so that you know what's going on. But let's just say this is a number. Okay? We computed that number by doing the integral. On the right side, when you do integral from negative pi to pi of a0 times cosine nx plus a1 times cosine x cosine nx plus b1 times sine x cosine nx plus a2 cosine 2x cosine nx plus b2 sine 2x cosine nx, and then keep going. Okay, what would this integral be? Cosine nx. Well, if cosine nx is integrated over its period, it's the same amount of ups and downs, right? So they cancel. Same with the sine. If you integrate sine nx or cosine nx, it will just give you 0. Okay? So that's going to be 0. Okay? What about this one? What would this be? Cosine x times cosine nx.
0 or pi.
0 or pi. When do you get pi?
And
M equals N.
When n is equal to 1. Right? So you can turn that around. Eventually, this 1x, 2x, 3x will have the same number as n, right? So you're going to get an times pi. Right? All the others will be 0. How about sine times cosine? That's always 0, right? So all of this will cancel out to be 0, and the only non-zero thing would be an times pi. Okay? So here's a nice formula that you get. You get that an must be 1 over pi times integral from negative pi to pi of f of x cosine nx dx. Okay? And then bn will be 1 over pi integral from negative pi to pi f of x times sine nx dx. Now there's however, one more thing. To get a0 by itself, you don't want to multiply anything. You can just integrate both sides from negative pi to pi. Then all of these will have integration 0. Right? On the other hand, if you integrate a0 by itself, what would you get? It would be a0 times 2 pi. Isn't that right? Okay. So you're going to get, unfortunately, I'll have to delete this. A0 is separate. This will be 1 over 2 pi times negative pi to pi of f of x dx. Okay? So that's the result of the Taylor series, not Taylor series, keep getting confused. Fourier series. Okay? Fourier series says that if f of x is defined from negative pi to pi, and you compute these values, then f of x is equal to summation, a0 plus summation from n equals to 1 through infinity of an cosine n pi x plus bn sine n pi x. Okay? So that's the Fourier series. Now this has some limitations. So in the Taylor series, I said, well, if you write down the Taylor series of a function and you plug in values both sides, they're equal. That's not 100% correct. One requires that the other side has to converge, because infinite series may not converge. So if it doesn't converge, then it might not give you the value. If it does converge, and there's some other error estimates there, you can show that they convert, they agree on they produce the same value. However, there's something fishy about this identity. This is the problem with this is that if you have, say, you have a function that's like 1. I need a function from negative pi to pi. So let me draw from here negative pi to pi. Let's say you have a function from that's constant from negative pi to 0 as negative 1. And then it's 1 here. Oh, I need open circle at one of them. Let's say this is open. Okay? Like that. And let's say we computed this, which is possible. We can do that, right? But then think of this other case. What if instead you put this as the closed circle and this as the open circle? Now you would get the same exact values for a(n), bn, and a0, wouldn't you? Right? You would. Because changing the value at just one point is not enough to change the value of the integral. In fact, you can change even places like here and put some random value here. Right? And that's not going to change the value of a(n), bn, and a0. Okay? So that this is definitely not always true. There's something going on here, and the correct way to say it is that if you say the right side is g of x and the left side is f of x, what's happening is if you subtract the two, take the absolute value squared, and you integrate from negative pi to pi, it has to be 0. Okay. That's the more technical way to say it, which is another way to say it in a very technical way is to say that the two functions are equal except for a set of measure 0. But that's like measure theory and all that. I mean, if you ever take mathematical analysis and you feel like, oh, why are they talking about like all these measure theory and like L2 space, LP space, what is this all for? It's because of all these technicality. If you learn that, then you'll be able to describe what's happening here in a more technical way. That's the reason why you learn that course. But for us, let's just dumb down things a little bit. Okay, so first of all, we're just going to limit ourselves in understanding the Fourier series not as any function in L2. We don't even know what L2 is, right? So we don't even care what L2 is. We'll only limit ourselves to functions that are piecewise continuous on this set, whose square integrals are 0, so that you don't have things going to infinity too fast. And then in that case, any singularity, so let's say we don't even want infinity, something going to infinity, okay? So in that case, there are only two types of discontinuities. These are called what? Removable, right? Yeah. So for any removable discontinuity, we just remove it, we just make it continuous, right? But there are discontinuities that are not removable, like this one. What is this called? What kind of discontinuity? You learned this in Calc 1. It's called a obvious name. It's called a jump discontinuity, right? Okay, that was easy, right? Okay, so if you have a jump discontinuity, okay, and what happens is that for such functions, where only discontinuities are jump or removable. For removable, you just remove it, make it continuous. For jump, what happens is that the series on the right side will eventually converge to the middle of the jump. Okay? So that's another theorem that you can prove. I don't think it's that interesting, so I'm not going to prove it. But that's something that you can prove in here. Okay? So if you have a function that's that has a jump discontinuity, let's say there's a jump here, then if you take the Fourier series of this, then that Fourier series will agree with this function exactly, except right here. It's going to have a jump. Oh, there's actually another thing that's going on here. See, the right side is periodic from negative pi to pi. So when you have this function represented like this, on this side it views this function as a periodic function. So another thing that the Fourier series is doing is it takes this function and treats it like a periodic function. So you just copy and paste, Control C, Control V. You know what I mean? Yeah. The way you write all your English papers, not these with ChatGPT. All right. Okay. But anyway, right. So Control C, Control V, Control C, Control V. Right? Yeah. You do that. It's a periodic function, left and right. Right. And then because of what I just said, there is a jump discontinuity which was not which you didn't know it had. If you do the series on the right side, you see that it's right here.
Hi, Professor.
Yes.
If we do the Fourier analysis, right? Is it or transform?
Fourier transform is slightly different.
Analysis.
You don't do the integral over a
So the
finite
function will
domain,
be
but infinite domain.
looks continuous, right? After the Fourier analysis. Just this case.
Is that right? If you take Fourier transform of a discontinuous function, would it be continuous? I don't know. Sorry, I should know that the answer. But embarrassingly, I don't know. Yeah. Huh?
Just this case.
This is not Fourier transform. This is Fourier series. In that case, a Fourier series of a discontinuous function will still exhibit discontinuities with the property that anytime it sees a jump, it will give you the midpoint right there.
Okay.
Yeah. So it still has a jump discontinuity. Now, this is actually called Fourier transform for applied mathematicians, because when you do calculations with computers, you really can't have infinite domains, right? So if you just have like finite domains with not all the points, but like finite points in a domain, then Fourier transform or Fourier series doesn't look too different. So they just call this Fourier series as Fourier transform. If you're ever doing like computer science, for example, when you do image processing, this will be called Fourier transform. And this here, you have to think Fourier every time you watch a YouTube video or you listen to music on Spotify. Because internally what's going on these things is like, videos and images and audio, these are digital data that consumes lots of memory. So for example, one movie barely fits in a 2 gigabyte DVD, right? But that's even after compression, right? The original one, when the movie studios take pictures and store in a lossless format, they could be like 100 gigabytes. But on a YouTube, those could be just, say, 500 megabytes. So it just goes down by a lot. And that's how you're able to watch it. Trying to listen to music or watch videos without Fourier series, Fourier transform will be impossible. What it does is, just like how Taylor series truncates something and it gives you the approximation. So let's say fx is a function, or I just have a one-dimensional function, but images are two-dimensional functions, right? And movies are three-dimensional because there's a time, right? So you can have functions that are three-dimensional, and you can still take the Fourier series in three directions if it's three-dimensional, or two dimensions if it's two-dimensional. So there's a 2D Fourier transform, 3D Fourier transform, you name it, you have all of that. And what you do is, let's say this is your favorite clip in YouTube, right? Okay. And YouTube doesn't store the original one. It takes too much memory. What they do is they take the Fourier transform, they truncate it at some point, because if it's very high frequency, people don't notice the difference, right? And then they just store that. And that can reduce the data by like 10-to-1 ratio. And then there are some other ways to compress, and those can reduce further if it's a video, because when you have a moving image, the image right before and right after doesn't change that much. So use that as well, and that's how you can watch any YouTube video. So that's Fourier transform.
Could I say that the fx is just an analog signal? And
yeah. Well,
and that is a digital signal.
Yeah. Okay, so you can say that, but in reality, we never can store analog signal faithfully. So what it does is it's a digital signal with very fine detail. Okay, but then on the right side, you have a digital signal where you truncate the high frequency and you have a less. So if you reduce the bit rate, the image quality gets downgraded.
But the original way we record music is just analog signal, right? So, but
so, okay. Well, when in the days of LP, you would say that you're recording analog signal, but not really, because that still is not a faithful representation of the music. Yeah. But let's say you have a digital, faithful digital copy of a music. Then it's either 48 kilohertz or 96 or 44, something like that. It's like you chop off that 1 second into 44,000 equal parts, and then you record its movement up and down. But that, like, say, a 3-minute song would be about 30 megabytes. But then you take the MP3 version of it, which does this. You truncate the high frequency that way. It reduces to 3 megabytes. So that's the revolution. Everyone here are enjoying what Fourier made for us. But in this class, I'm introducing this because we used it for a heat equation, right?